Rungwe Volcanic Province, East Africa.
Thank you. Yeah, I'm from Virginia Tech, Njinju. I'm working with Dr. Stamps in collaboration with other scientists like Rungwe, Estela Tekwana, and Tahiri Ragwana. So the figure you see, the image you see in the background is a crater lake called Lake Ngozi. It's part of the Rungwe Volcanic Province in East Africa, and this talk will focus on investigating the source of deep metal generation within this volcanic center. So I will start this talk by showing you a very busy map. Busy, but very interesting because it's showing how each continent have been busy trying to rift apart. However, there have been several failed attempts for the continent to rift. So breaking up is hard to do. Yeah, and rifting has, there have been several failed attempts since Precambrian. Example, we have the mid-continental rift here in the US that failed around 1.1 billion years ago, during as one of a failed arm of the triple junction during the separation of Amazonia from Laurentia. Despite the fact that we've had several failed attempts, there have been some successful attempts. That's why we have our spreading ridges and our continental margins. Some of these reefs are still active, and I will show some highly studied ones. This includes the Rio Grande Rift here in the US. We also have the East African Rift, and we have the Barika Rift in Asia. We will note that these rifts are narrow and elongated. We say the deformation is localized within a narrow region, and we call them narrow rifts. So the narrow rifts are characterized with strain localization. However, we have some rifts whereby the deformation diffuse is spread over a wider region. The common ones highly studied include the basin and range and the agent rift. So why is it very important to study continental rifts? Yes, go. Why is it very important to study continental rifts? We know most rifts have a thick sedimentary deposit that holds hydrocarbon deposits. So an example here, I have a drilling site in the Albertine Rift, which is part of the East African Rift system. Also, those sedimentary basins host records of past climates. And continental rifts are characterized most often with volcanic eruptions that release a lot of carbon dioxide gases that will lead to global warming. And there are also sites for volcanic and earthquake hazards. Despite the societal importance, there are also some other scientific importance of continental rifts. We know continental rifts form a very important component of the plate tectonic paradigm. They are actually precursors of no oceanic lithospheres. Yet we have very fragmented understanding of how rifts form. Studies suggest three main tectonic forces, and the most common or dominant one is slab pull at subduction zone, where the weight of the subducting plate stretches and thins the lithosphere. We also have buoyancy forces due to gradient in gravitational potential energy, where we have high topography. And in the offshore setting, it happens in spreading centers or spreading ridges. And then we have mantle traction at the base of the lithosphere, whereby the mantle exerts shear stresses that tends to stretch and thin the lithosphere. Let's put some numbers onto these different tectonic forces to better compare them. Studies suggest that the slab pull forces are generally greater than 15 teranewtons per meter, while the buoyancy forces are less than 5 teranewtons per meter, and mantle tractions generally less than 3 teranewtons per meter. So we see that slab pull is the most dominant. Now look at the African continent is surrounded by spreading centers. There are no slab pull or subduction zones that can contribute slab pull forces. Yet Africa is rifting apart. In the red box, we have the East African Rift system. And studies suggest that in the absence of this dominant slab pull force, the remaining tectonic forces, that is the buoyancy force and the mantle traction, are inadequate to rupture a strong thick lithosphere. except there are some weakening mechanisms within the lithosphere. And studies, Buck did a comprehensive numerical study on the strength of lithosphere for 2 different scenarios. The blue here is in the case where there is no melt within the lithosphere. And here we have a plot of the forces versus the lithospheric thickness. And the red here is a scenario where we have melt within the lithosphere. So assuming a 60-kilometer thick lithosphere, and we project, we see for the lithosphere without melt, the strain is greater than 20 teranewtons per meter. That's very strong, hard to break. When we have melt within the lithosphere, it's so weak. It's just about 3 teranewtons per meter. And the available buoyancy forces of 5 teranewtons per meter is enough to rupture a lithosphere in case there is melt within it. This suggests, or this is the basis for the magma-assisted drifting model, which suggests that magma helps or enables drifting. And the magma-assisted drifting model is characterized by repeated intrusion of melt within the lithosphere, either from an upwelling asthenosphere or from plume head materials that thermally weakens the lithosphere, making it easier to rupture. And most often, these magma-assisted drifting models are characterized by surface expression of volcanism or magmatism. And it's validated in the eastern branch of the East African Rift System. You have numerous volcanic centers, the red triangles, which suggests magma is playing a very important role in rifting in the East African Rift System. We also have a widespread flood basalt. However, the western branch is magma poor. We see very sparse volcanic centers. And the southernmost one there is the Rungwe volcanic province, where this study is focused. So this study is focused to better understand the role of melt in rifting. There's need to investigate deep melt generation. So we focus on the Rungwe volcanic province. And in a previous study, we developed a lithospheric modulated convection model that incorporates melt generation. And yeah, we're happy to be able to generate melt. The melt fraction is generally less than 1% at depths of 130 to 150 kilometers. However, for very elevated mantle potential temperatures, which suggests there's a possible heat source beneath the lithosphere in the Rungwe volcanic province, maybe from plume head materials. And how can we constrain that? Seismic can provide a way to constrain that. So there's therefore need for further investigation of deep melt generation beneath the Rungwe volcanic province. So we hypothesize that the compression melt plays an important role for melt generation beneath the Rungwe volcanic province, and these thermal anomalies can be due to plume materials. Yes, the seismic tomography model by Emmanuel et al. Is characterized by this low velocity zone that rises at depth from the west and flows laterally to focus beneath the Rungwe volcanic province. This low velocity zone, this is a characteristic flow pattern that might suggest the presence of a plume beneath the Rungwe volcanic province. So there are some scientific questions that remain unanswered. Is there melt actually at depth beneath the Rungwe volcanic province? And what's the source of that melt? So in order to answer that question, a little bit of maths, we model a time-dependent tomography-based convection beneath the Rungwe volcanic province using the open source finite element code or ASPECT. ASPECT stands for Advanced Solver for Problems with Earth Convection. So we are actually solving the velocity term or the velocity field in the momentum conservation and the mass conservation equation. And in the momentum conservation equation, the viscous forces and the pressure gradient forces are balanced by the buoyancy force, which is the main driving force for mantle convection. And important thing we do here is we're assuming, or we're using an elastic lipid approximation, which is based on 2 assumptions. That there's small density perturbation in the model can be approximated by Taylor expansion about a reference temperature and reference pressure. And the second assumption is those density perturbations are so small such that they are neglected in the mass conservation equation and in the energy conservation equation. Since we're interested in modeling melt generation, we also simulate the temperature evolution in our model by solving the energy conservation equation. So we also solve for the temperature T. And in the temperature or in the energy conservation equation, energy or heat transfer by advection and heat transfer by diffusion are balanced by different heating models. And an elastic liquid approximation also checks that there is shear heating and adiabatic heating. But we, however, include the latent heat because we are generating energy. So the one important point in our model is how we constrain the initial temperature condition. So we use the lithospheric structure of our region that is extracted from the Fish Week 2010 model. Fish Week determined the lithospheric structure in Africa from shear and surface wave tomography. So in the Rungwe volcanic province area, we see the hot colors here represents regions within lithosphere, about 100 kilometers. And the lithosphere gets thicker southward towards the Malawi Rift, reaching up to 200 kilometers in places. So we use this lithospheric structure to constrain the initial temperature in the lithosphere, and we assume a linear geothermal gradient in the lithosphere with temperature increasing from the surface at 298 Kelvin to the temperature at the base of the lithosphere, which is constrained by the mantle potential temperature. So the mantle potential temperature beneath the Rungwe volcanic province has been constrained from studies, geochemical studies by Rungwe et al. And we will use those constraints in this study. So how do we constrain then the temperature at the base of the lithosphere or in the sublithospheric mantle? So if ZLAB is the depth to the base of the lithosphere, then if we have Z that is greater than ZLAB, then we are now in the sublithospheric mantle. So replacing ZLAB with Z, we'll get the background temperature of the sublithospheric mantle. The most important part of this study is how we constrain excess temperature in the sublithospheric mantle. So we're using shear wave velocity anomalies, and that's where this study actually gets its name. The name is because we use shear wave velocity anomalies to constrain excess temperature in the sublithospheric mantle. So this is a shear wave velocity anomaly from the Emmanuel et al. Model, and this is it shows low velocity anomalies beneath the Rungwe volcanic province. So we convert this shear wave velocity into excess temperature in 3 steps. The first step is we multiply the shear wave velocity perturbation by a velocity to density conversion factor of 0.15 to get an equivalent density perturbation. And the next step is we divide the resultant density perturbation by the thermal expansivity and multiply by -1 to get the excess temperature in the sublithospheric mantle. And according to the profile AA prime that we see, you can see that the excess temperature can go up to 250 Kelvin beneath the Rungwe volcanic province. Those are plume-like excess temperature based on petrological studies, which suggests actually that there is possibly plume material beneath the Rungwe volcanic province. The third step, we add this excess temperature onto the background temperature to get the final initial temperature in our model that we show in 3D. So we can see in 3D also our model geometry that extends up to 660 kilometers depth. We also show a 1D depth profile of our initial temperature condition. And the blue here is the background adiabatic gradient. And the effect of adding the excess temperature, you can see a positive shift in the adiabatic gradient. Another important part of our model is how we constrain the rheology. So we assume a very rigid lithosphere by giving a viscosity of 10 to 20 parts per second, while in the sublithospheric mantle, we assume a composite rheology, in which the viscosity is the harmonic average for the viscosity of diffusion creep flow laws and dislocation creep flow laws of dry olivine. We also, since we are modeling melt, we also implement porosity weakening in our model. So the next and the big part of our model is how we generate melt, or partial melting. So we use the melting parametrization of peridotite after Katz et al. In 2003 melting is based on a simple concept. Melt will be generated if and only if the geotherm crosses the solidus. So in a case where the geotherm does not cross the solidus, no melt will be generated. But if the geotherm crosses the solidus, then we have melt generated with melt fraction proportionate to the temperature in excess of the solidus. And in a very extreme case, that the geotherm crosses the liquidus, then we'll have 100% melt, or a melt ocean, which is unrealistic. It doesn't happen in nature. Here, the solidus and the liquidus, they have a quadratic relationship with pressure. So we have a diagrammatic representation of the melting parameterization. You can see that the solidus and the liquidus are indicated in red, and the geotherms in blue and green. And melt will be generated if and only if the geotherm crosses the solidus. So the geotherm is constrained by the mantle potential temperatures, and in the Rungwe volcanic province, the mantle potential temperature ranges between 1693 and 1723 Kelvin. So we test a wide range of mantle potential temperature in this study. And our results, interesting results. This is a result of our tomography-based convection model. The hot colors represents regions with upwelling, and the cold colors represents regions with downwelling, and the black arrows represents lateral flow, horizontal flow. So at a depth side of 250 kilometers, we see upwelling happening adjacent to the Tanzanian craton, flowing towards the Rungwe volcanic province. And at shallower depth, the upwelling tends to be very focused in the volcanic center, and it's characterized by radial horizontal flow patterns. This is a characteristic rapid upwelling, and good enough, this upwelling generates compression melt, reaching with melt fraction generally less than 1% beneath the Rungwe volcanic province at depth of 130 to 150 kilometers. So let's synthesize all of these observations in one figure. Yeah, this is a given figure that summarizes everything. So the top panel here is our model for tomography-based convection, and we compare our results in a case where the model is driven by simply the lithospheric architecture, like variation in the lithospheric thickness. And the main goal of comparing these two models is to see if adding upper mantle constraint would improve the mantle flow patterns. So the top panel here has upper mantle constraints in terms of shear wave velocity propagation. So the white arrows here shows the mantle flow patterns, and it's superimposed on the background temperature. And we also have melt fraction plotted. So we see melt is generated beneath the Rungwe volcanic province in both cases. But then an important point to note are some interesting flow patterns revealed in the case with upper mantle constraint. We see upwelling happening underneath the Tanzanian craton. That is not happening in the case we do not include upper mantle constraint. We also see this corner flow adjacent to the Bangwelu block. That is not very evident in the case of a lithospheric modulated convection. So we think, and we're happy that we have developed an improved mantle flow model that resolves some flow patterns that were not constrained from previous studies. So in our conclusion, we conclude that there is melt beneath the Rungwe volcanic province that might be sourced from plume materials. And this is because we have excess temperatures of up to 250 Kelvin that is characteristic of plume. Also, geochemical studies from by Hilton image suggests helium-isotopic ratios reaching up to 15 RA. Those are plume-like ratios. Even studies by Ronnie Tar suggest very high mantle potential temperatures that are plume-like. And we also observed that this study includes upper mantle constraint in terms of shear wave velocity perturbation and reveals previously unresolved mantle flow patterns. So I think it's an improvement. And for the future work, we want to model how melt will migrate through the lithosphere onto the surface to erupt at the surface. And there are still some outstanding questions that remain unanswered. How does magmatism enable strain localization in the lithosphere? The thing that question is not well answered. And what is the dynamic feedback between magmatism and lithospheric deformation? Which one happens first? And how did that actually happen? So I'll end here for now. Are
there any questions? Emmanuel?
So you use the seismic velocity to convert density.
Yes.
I was wondering, that's sort of an important step because you're assuming thermal expansion. If there is melt present, that will perturb the seismic velocity. And so different relationships will arise. Yeah. Right. So how does that affect the story? And that's important because you're both generating shear due to the upward, which can, for the continental rifting stories, contribute to the shear, but it's also generating gravitational potential. That's an important step there, right?
Yeah, this is one of the most important steps in this study. Yeah, so generally, there's a lot of assumption that goes into conversion, the conversion of shear wave velocity perturbation to temperature, because this assumes that the shear wave velocity is mostly due to temperature anomaly. But we know that that's the shear wave velocity perturbation can also depend on compositional variations and even the presence of melt fluids. So that's one of the limitations. And in another study, we are trying to answer or address this same question by doing joint inversion of other data sets to better constrain the density structure.
Right.
So,
yeah, I had a kind of a similar question, but maybe in a different way, which is, since you did all this work converting the velocity into what you need in your model, it feels like you have all the tools to then take your models and convert them back to velocity in a way to guide our thinking about what we might be able to observe or what the anomalies would look like. Have you thought to do that? Or
yeah, that's a great question. I've been thinking on how to do that. Yeah, and I've not done that yet, but there's thoughts on how to do that. Like convert our model output, try to invert it to see what kind of observations we can get, what kind of models we can get from independent scholars. So it's something I've been thinking how to do.
all right. Thank you very much. So let's move on.